Hello, everyone. Welcome to our talk. My name is Srdja, and this is Tomislav. And we were programmers on the tech demo that you saw in the keynote. And today, we wanted to tell you what we did, how we did it, and share you a game developer's perspective of what it's like of using new Unity technologies. A little bit about us. We're from Nordeus, an independent gaming company based in Belgrade, Serbia. Our flagship game is Top 11, the most popular online sports game in the world with over 150 million registered users. Right now, we're developing a mobile-like game for mobiles called Spellsouls Duel of Legends. And we based the art style and used some of the assets from that game for the tech demo itself. But all of the gameplay and game logic and code and everything was written from scratch using new Unity technologies. Just a quick shout out to the team that made the demo. Besides these people, the entire company helped, and we couldn't do it without them. So thanks to everybody. And without further ado, let's start with the demo. Just show you my favorite thing to do in the demo. Maybe even more zoomed in, so you can really see them fly. Yes, we had a lot of fun coding that. Okay, so I hope you all attended Joachim's talk. We're not going to go over how the system is implemented in Unity side, because we hope you heard him. We're going to go more from how we implemented our gameplay logic and how we use that system to make this possible. So just a quick refresher. I swear this is the only really basic slide. But the thing with object-oriented programming and the way that we programmed Unity games before is that we always have an array of data which has pointers to the actual data which exists in the heap at some random memory locations. And this is definitely not good for CPU utilization. And the really cool thing about these new technologies is that they give us an extremely easy way to switch from object-oriented programming to data-oriented programming, where all of the data is linearly in memory. And this is a really big paradigm shift and a really different way of thinking. But all of the AAA engines internally, including Unity, use this way of processing data because it's simply much, much more efficient. And the entity component system gives you a really easy way to do this yourself and gain a lot of performance. But besides that, it also allows you to use object-oriented programming, the old way of programming things in Unity, when you need to. And for the entity component system, it's in 3 parts. This is, for example, our unit transform data. It's used to place units in the world and rotate them around. Since we were using ECS purely, we didn't have access to regular transforms. So we created data components and operations on them that act as transforms do in Unity at the moment. Once you have components, you simply need systems. For example, this is a very big simplification of our movement system. It simply goes through the array linearly and samples the nav mesh at that position and moves the units forward. And finally, for the last part of ECS, how these components are combined. They're simply archetypes. For example, minion is our unit on the screen, and it consists of multiple components. For example, our minion have transform data, variable minion data, constant minion data, and rendering data. And the really cool thing is that, actually not the really cool thing. What I really like about this is that we never did data-oriented programming before. And once we started, it looked really daunting. But within a week or 2, it finally clicked, and we were able to write much more performant code than we were able to do before using this entity component system. And after that clicked, we went into using jobs. And Tomislav will tell you a little bit about all of the game logic that we implemented inside of jobs.
Thank you, Srdja. So let's do a quick rundown through all the jobs we have in our game. I counted about 25 jobs, and many of them are actually small housekeeping jobs. There are only a few that are really heavy and do the heavy lifting. We have path finding. We do it on 2 levels, high-level path planning and low-level path finding. We do the collision detection and resolution. We have some minion behavior. They decide who to attack, when to attack, and which animation should be played on the minion. Then we have a system that deals with arrows and flying units. And of course, at the end, we have to render all of that. So let's show you our path finding and how we did it. Yeah, switch. So as I said, we have high-level and low-level path finding. And we use the low-level nav mesh API, the new batched version. OK. Can we kill the audio on the... Yes, thank you. OK. So minions move in formations, and we first do the path finding on the formations. As you can see, they just do the basic high-level path planning. The nav mesh is then used to do the low-level path finding on the units. When units get lost from a formation, then they try to find their way back to the formation using the path finding. And when they're in the formation, then they moved along with the formation, so we save some time there. Then we need to have some units that bump into each other, and we have to do the collision detection. We use the spatial hashing as the best technique to do the collision detection on such high level. Basically, that means that we take a minion's position, put it in a bucket, calculate a hash of that bucket, then we use a native multi-hash map and put a unit in a hash map. Then there are 2 ways we can go about this. We can put a minion in all the buckets which overlap with the unit, or we can, when we do the collision resolution, we can traverse all the surrounding buckets around the unit. We chose the second option. The minimum cell size has to be at least 2 times the radius of the biggest minion. Our collision resolution is also really basic. It's inspired by smoothed particle hydrodynamics. So basically, our units are just particles that behave like fluids in this fluid simulation, and there are some forces that repel them. So that means our minions are smooth. They're deployed. Then we have to kill off those units somehow. And there are two ways to kill a unit, by sword or by an arrow. We have several thousand arrows on the screen at any given time, and we use the new batched raycast API from Unity. Basically, you can query a batch of raycasts and execute them in parallel. So arrows shoot raycasts all the way down. We figure out when they hit the ground. When they hit the ground, we calculate their hash, and then we just take the first minion from the bucket and hit it with an arrow. That was good enough for our case. And as mobile developers, we are really excited about these new batched APIs, which means that Unity is actually exposing some of the engine stuff to be accessed on the second thread. I'm personally most excited about doing procedural mesh generation on other threads. Another cool thing about the arrows is that they are not pooled. We basically destroy all of them and instantiate them in a single frame. We can do that because we use the entity component system, which does not have the overhead of a transform, of a game object, or a renderer, and we have complete control over it. Actually, switch back. Yeah, I want to give you a little tutorial about the ECS. 1 minute tutorial about the ECS. So how do we make units fly? I hope you can see. This is all of the data that is attached to one unit. And for example, we have here minion something data, minion data. Let's say it's minion data. What we do in the ECS, we just remove the minion data component, attach flying minion component. The ECS system automatically picks it up, puts it in a proper array. Then the job system picks it up, and the flying job system, which controls the arrow, also controls the flying units. It's that simple. Another awesome concept, the unsafe code. I really like unsafe code. As mobile developers, we're also very excited about this. You don't have to use the job system or ECS. You can now use the native collections that are provided by Unity, so you have more control over the memory. This unsafe utility actually helps you write a little more safe native collections. You could do that previously with unsafe code and pointers. Now we have support from Unity, which is awesome. Unity provides you, well, actually we heavily use native arrays, native queues, and native multi-hash maps. Okay, unsafe stuff is cool, but also safety is really cool. Joachim talked about the safety system in C# job system. So if you're about to make a race condition, Unity throws an exception. And that made us at least 2 times faster when designing the system. But I have to give a shout out to the previous slide. You can circumvent the Unity's built-in safety system to do some more awesome hacks, but I don't want to talk about it now. Then we as basic data-oriented programming noobs, had to discover some concepts. We had a problem where there are multiple minions hitting another minion, or multiple arrows hitting one minion. So we couldn't properly decrease health on a minion because multiple sources were attacking him. First solution we tried, we made a concurrent data structure that allowed you to do that. This turned out to be too slow because of all of the locking that is happening and everything is executing in parallel. And it didn't scale very well across the cores. When we started thinking more about data-oriented and more parallel, we tried to start avoiding locks. So we were thinking about data and jobs as operations that transform data, and the program is just one big pipeline that transforms data. And then we got a better solution, that is you can queue up all of the actions in the native concurrent queue, and then kick off a separate job that goes through the queue and executes all of the commands. This introduced a sync point on the main thread, but overall made the system faster. Unfortunately, only action we have in the demo is decrease health on the minion action, but you could extend it to do more stuff. Then, if you move your jobs around smartly, and you can live with 1 frame latency on your input, you can basically move your jobs in such a way that things are executing near the end of the frame and overflowing into the next frame. These Rakic jobs and these preparing jobs for targets actually overflow to the next frame, and we have 1 frame of latency, but we achieved much better parallelization that way. And my favorite slide on this presentation is the burst compiler. Basically, for us developers, this means free performance. We didn't believe them when we came to the Copenhagen office. They were talking about 14x increases. When we compiled the first job with the burst compiler, it gave us 20x increase. That doesn't translate to 20x increase in frame rate, but it is pretty awesome. Let me demonstrate that.
It's still, oh, okay.
Okay. Use burst, don't use burst. Okay. You see it, it's around 40 now. Use burst, it goes back to 60. Okay. 20. 50. Awesome stuff. Okay, so I've talked about simulating minions, but we also had to animate and render them, and Srdja is going to tell you more about it.
Yeah, so it's not exactly related to the new technologies Unity is developing, but we think it's really cool to be able to render this many minions, especially in the editor as well. So we wanted to say a few words of how we actually did it. And the thing is that at the beginning we tried using instance rendering, but we very quickly realized that using instance rendering is not fast enough to render this many units because the units still have to go through the culling system and some other systems before they're actually drawn on the screen. So we dug a little deeper and saw that we could use indirect instance rendering. Since we're mobile developers, we never actually got a chance to use that because it's not supported on most devices. But since we're developing a PC game now, it was awesome. We can use whatever we want. And indirect instance rendering is really cool because you let the GPU do most of the heavy lifting. All of the CPU systems like culling and such are completely bypassed. And in our first test that we did, we found it to be at least 10 times faster than using normal instancing. The thing is that it's also called procedural instancing when you write shaders. And when you're drawing instance units, you need to specify their positions. In normal instancing, you specify that in arrays, but in indirect instancing, you would create compute buffers, which are similar to arrays, but can also be written and read to from compute shaders. But since we're using the job system, we thought, why don't we try doing that on the CPU instead of a compute shader? And that actually turned out to be a very good decision, and I'll tell you about that in like 2 minutes. But we were filling compute buffers from jobs, and it was extremely fast. Like filling all of these compute buffers for 100,000 units is, I think, less than 10 milliseconds total on all cores, so like 0.5 milliseconds per core on this machine. And the thing is, when you're using instancing, you have to use the same mesh for drawing. And that's not compatible with animating because normal skinning will transform the mesh, so you would end up with 100,000 different meshes in different poses. So we decided to do skinning in the vertex shader, GPU skinning. And since we're drawing all of the units of the same type at once, so fun fact, all of the units here, all 100,000 units are rendered in 16 draw calls total. and the environment is 800 raw calls. So we did the skinning in the vertex shader. How we did that? Well, we took all of the animations at the beginning, at starting the game, and for all of the animations, we sampled them at a certain frame rate and baked all of the bone positions and translations into textures. All animations for the same minion type into the same texture, so we could render all minions of the same type together, no matter what animation they're playing at the moment. And the thing is, since it's sampled at a certain rate that's lower than 60, we need to do some interpolation. And the standardly bone position transformation scale is represented by matrices, but matrices don't interpolate very well. And we also wanted to use the GPU hardware as much as possible because we have a lot of units, and doing things suboptimally would break our frame rate. So what we actually did, and what I suggest that you search for if you want to do this, we didn't use matrices, we used something called dual quaternions. It's a fancy math system that allows you to describe translation and rotation with two quaternions, and quaternions can actually be linearly interpolated, even with bilinear filtering used by GPU hardware. And for example, I just wanted to show these blobs. These are actually textures that describe how the bones are translating. Each row is a separate bone and how they're rotating by quaternions. And another pretty fun fact, at the keynote, the screen that the demo was playing was 5K. And we were actually GPU bound and not CPU bound, even on a Titan X. So to sum it a little bit up, what you could do better to actually run more than 100,000 units? Well, the thing is that we wanted to actually stress the job system a lot, so we didn't do a couple of optimizations that you could do to make it run better. For example, we mentioned frame latency. Well, you could do double buffering, and when you do double buffering, you can actually squeeze jobs even further together and achieve even better multi-core utilization. And if you're feeling extremely adventurous, you can actually also do triple buffering. The thing with triple buffering is that when you're using triple buffering, you can actually run the simulation at a much lower frame rate. At the moment, the simulation is running at the same frame rate as the rendering, so 60 FPS. And all of the collisions, all of the path finding, everything, all of the attacks, updates are done at 60 FPS. But you could actually do them at much lower, for example, at 5 times lower than your target frame rate. And then you can do them over 5 frames, which means that you could theoretically run 5 times more units, so like 500,000 units. And yeah, that's pretty much it. We just wanted to give you a quick overview of what we did and how we did it, and I hope we have some time for questions. Thank you.
It looks amazing. I love it. I was curious with this new ECS paradigm, how this might affect your workflow with artists, specifically things like prefabs versus entities and those kinds of things.
You can mix and match ECS and the old mono-behavior stuff. We actually have spells which we pulled from the original game. They use standard mono-behaviors. And funny thing that you mentioned this, the slowest thing in production of this demo was merging prefabs.
Nice. Thank you.
Yeah, I just wanted to show that we actually do have a scene here with the entire hierarchy. The artists were doing everything the old-fashioned way, but we wrote systems in entity components. So, for example, you also have a timeline here with everything you would expect a timeline to have. And the artist did everything with game objects, with transforms, with animating camera, animating lights. And we did the simulation code in ECS, so mixing and matching works really, really well. We got the performance we needed, and the artists got the tools that they needed to do this.
Could you go a little bit into into more detail about how you sample the textures to be able to get the animation data out and then bake it back into the verts for animating the units?
Yeah, okay. At the beginning, when we start the game, we have a list of animations that the units will play. We read all of the bone positions and translations at certain frame rate. That we get matrices back. Then we transform each of those matrices into dual quaternions. We get two quaternions, one for position, one for rotation. And we write those in textures. So the first column of the texture is at the first sample position, and each row is a separate bone. And then we do that for all of the animations. We put them together in one texture. And are you okay with that part? That's the CPU part, yeah. Okay? Now the part in what the job does. So when we play animation, the only thing that we need to know is where we need to read from that texture, which column we need to read depending on the time of the animation. That's something that we do in jobs. We increase it by delta time that has passed. And we pass that one parameter into the shader per instance, because each instance can play a completely different animation at a completely different time. And then we simply sample the texture with bilinear filtering. It interpolates the quaternions. And we apply the translation and rotation quaternions to the vertices themselves.
And at what point do you sample those textures in your shader?
In the vertex shader at the very beginning. And then we transform the vertex, which is in object space, using those transforms. And then we transform it into world space using the normal world space matrix.
Okay, thank you.
No problem.
Another texture animation question. So
Yes.
how expensive is this operation, both in space and time?
Okay. In space, it will be slightly more expensive. But we actually can also use it for our mobile game. So I think it's fine unless you have a lot of animations. The thing is that you don't get all of the flexibility of Mechanim because you have to do blending of animations manually and blend trees manually. As for the cost, I tested this on mobiles a lot, and this is about 4 times faster than matrix palette skinning, the standard matrix palette skinning. Especially since you can draw them instanced, which you cannot do with standard techniques.
Thanks.
No problem.
What are the limitations of this animation system that you're describing?
Okay. So you don't get the blend trees of Mechanim and stuff like that, like I mentioned before. Other than that, yeah, you don't get, you cannot blend a lot of animations together because it's very expensive per vertex if you have more than like 2 animations that you want to blend together. Other than that, there are not a lot of downsides. If you want to render units multiple times, then you have to do this operation every time you want to render the unit. In that case, it might be cheaper to transform it once and then render the transformed multiple times. But it depends on how many times you want to draw it.
Thank you.
No problem.
Okay. Thank you guys very much.